Welcome to section 9.5. In this section, we are looking at solving first-order linear systems of differential equations involving a defective coefficient matrix. We saw in the previous section how we handle cases with non-defective coefficient matrices involving the eigenvalues and eigenvectors that they produce. Now we're going to look at how we can handle these cases where the matrix is defective. So not every eigenvalue is pulling its own weight, and we have to try to make up that difference somehow. So we're going to start off by looking at an example and see how far we can get in this process. So if we take the determinant of the a minus lambda I, so that's negative lambda, negative 2, 2, and 4 minus lambda, that's going to give us negative lambda times 4 minus lambda plus 4, which gives us lambda squared minus 4 lambda plus 4, which is lambda minus 2 quantity squared. So this is all set equal to 0, which gives us lambda equals 2 and 2, or if you want 2 with a multiplicity of 2. So in order for this matrix to be non-defective, we would have to get 2 corresponding eigenvectors out of this. So we look at the null space. We get negative 2, negative 2, 2, 2. So if we simplify this, we end up with only one free variable. So we get our eigenvector as negative 1, 1. So we get our first solution, x1 of t, is e to the 2t times the vector negative 1, 1. But that only gives us one solution. And we have 2 eigenvalues, right? Same eigenvalue, but it occurs twice. We should be getting 2 eigenvectors and thus 2 solutions, x1 and x2. But we don't have that. So the question is, since A is defective, how do we get x2? And we're going to be specifically focusing on 2x2s and 3x3s only for the context of this section. So to get x2, we're going to try a solution that has this form. So that's e to the lambda t times w1 plus t times w2, where w1 and w2 are to be determined. So we're taking still the e to the lambda t times not just a vector this time, but a sum of vectors with a factor of t in there. That ensures linear independence as well. So substitute this form of x2 into x prime equals ax. And we end up getting, for the x prime, we get lambda e to the lambda t times w1 plus tw2 plus e to the lambda t times w2. That's a product rule because there's t's here and a t there. And that is equal to a times x, which in this case, this is the x. So a times e to the lambda t, w1 plus tw2. So if we're plugging this solution into our general form of our system, we're going to equate the corresponding terms to each other. So any term that is multiplied by t, so that would be anything like this one and this one, we're going to equate the coefficients of those t's, and then we're going to take all the ones that are not attached to a t, and we're going to equate all of those to each other. So for our t terms on the left-hand side, so we'll multiply that in here, but we get lambda e to the lambda t times W2 must be equal to, if we multiply that in there, the coefficient on this t, which will be a e to the lambda t times W2. And if you look at the relationship that they have here, e to the lambda t is the same in both. You could even technically divide that away because we know it will never be 0. And you're left with lambda W2 equals a W2. And that relationship tells us that W2 is an eigenvector. Okay, so W2 is an eigenvector. Okay, so it'll either be the same eigenvector that we saw before or some multiple of it, right? It'll have the same form as the eigenvector above. So that's what happens when we equate the t terms. Now let's look at the non-t terms. So that's going to be lambda e to the lambda t times W1 plus e to the lambda t times W2. So that's this one and this one. And on this side, that's just this. So equals a e to the lambda t times W1. We can get rid of e to the lambda t in all terms. Subtract this over. We would be left with W2 equals a minus lambda I times W1. Right? If we get rid of those and then subtract that over to there, and then we can factor out the W1. So we know W2 is an eigenvector, and W2 is equal to a minus lambda I times W1. So since W2 is an eigenvector, a minus lambda I times W2, so that would be a minus lambda I squared times W1. Right? Because W2 is a minus lambda I W1. So if we substitute that into here, that gives us this. That would be equal to 0, to the 0 vector. Okay, again, since W2 is an eigenvector. So when it comes to finding W1 and W2, we need to choose a vector W1 such that W1 times a minus lambda I squared gives us the 0 vector, but a minus lambda I times W1 does not give the 0 vector. Okay, so we need to choose a vector that when we multiply it by a minus lambda I, it does not give us 0, and instead will give us W. But then when we multiply it again by a minus lambda I, because that's squared right there, when we multiply it again, we should get the 0 vector out of that result. So I've got a little diagram right here. So we're going from W1 to W2 to 0. So W1, this is something that we choose. Okay, so we choose W1. When it gets multiplied by a minus lambda I, it gives us W2. W2 should be an eigenvector. And then when we multiply times a minus lambda I again, it should produce the 0 vector. And that's how our setup is going to look. And once we have W1 and W2, that gives us the general form of the second solution. Okay, so like with this example back here, we're going to revisit this right now, but we already found x1, so that first solution. Now we're going to need to find the second solution. So let's go, it's top of the next page. So return to this example. So we're going to have lambda equals 2. If we take a look at a minus 2I, so that's a minus lambda I, this is negative 2, negative 2, 2, 2. Then if we take a look at a minus 2I squared, so that's negative 2, negative 2, 2, 2, times negative 2, negative 2, 2, 2. We're going to get, so we go row by column, etc. So we get negative 4 plus, we get plus 4 minus 4. So 0. We get plus 4 minus 4. So that's 0. We get minus 4 plus 4. So 0. And then minus 4 plus 4. So 0. So this works out in our favor. We need to choose a vector W1 that when it gets multiplied by a minus 2I, it produces an eigenvector. But when it gets multiplied by a minus 2I squared, it produces the zero matrix, or the zero vector, excuse me. What we have here, a minus 2I squared, is already the zero matrix. So any vector times this would produce the zero vector. So that's good news, because that means that all we really have to be focused on is the first one. And as long as it works for the first one, it will work for the second. So our choice, remember the eigenvectors have this form, the negative 1, 1. So in our choice for W1, I'm going to choose 1, 0. Now, it is important to note, this is not necessarily the only choice. We pick this for simplicity. So this is not necessarily the only vector that's going to make this work, but it's definitely the simplest version of that vector to make it work. So if we choose that for W1, W2 is a minus 2I times W1. And when we look at the calculation, we get negative 2 times 1 plus nothing. So that's negative 2. And then we look at 2 times 1 plus nothing is 2. Essentially what this vector is doing is it's just taking the first column, negative 2, 2, which is a multiple of that eigenvector that we had back at the beginning. So this is an eigenvector. Okay, it is one of the eigenvectors of that same form. So this is a valid choice for W1. Okay, because it gave us W2 as an eigenvector, and if we were to multiply it by this, it would produce the zero vector. So that gives us our solution for x2. So that's going to be e to the 2t, and it's W1 plus t times W2. So that's 1, 0 plus t times negative 2, 2. So our general solution, so x of t, is going to be the linear combination of x1 with x2. So x1 we found on the previous page. So that's e to the 2t times negative 1, 1. Plus C2 e to the 2t times 1, 0 plus t times negative 2, 2. And that would be the general solution to this system of differential equations, where we have a defective coefficient matrix A, we are able to produce this alternative solution that still gives us, again, all real valued solutions and keeps the solutions linearly independent from each other and still gives us the proper amount of solutions. So we had a 2 by 2 matrix and we have 2 solutions here added up in the general. Now, if we have a 3 by 3, this process stays similar but gets a little bit more involved because there's more possible outcomes here. So for a 3 by 3 matrix, we have 3 possible cases, 3 things that could happen. You could get 2 distinct eigenvalues, so lambda 1 and then lambda 2, with one of those having a repeat. So you have lambda 1, multiplicity 1, lambda 2, multiplicity of 2, so it occurs twice. Lambda 1 produces its own eigenvector. Lambda 2 produces its own eigenvector, but not 2 of them. Again, if it produced 2 of them, this matrix would be non-defective, and we would just use the methods from the previous section. We wouldn't need to do anything different. So in this case, you have 2 eigenvalues distinct, and you have 2 eigenvectors. So this one is not pulling its full weight. It needs another eigenvector for its multiplicity. In this case, we can handle lambda 2 v2 exactly as in the 2 by 2 case. So lambda 1 v1 is done, and then lambda 2 v2, we do exactly the same format. Okay, so we're down 1 eigenvector, so we perform this same type of solution to produce that 1 extra that we need. Case 2, you could have 1 eigenvalue with a multiplicity of 3, and it only produces 2 eigenvectors. So we're still missing 1 eigenvector, and this case also proceeds just like the 2 by 2 case. Again, if we're down only 1 eigenvector, that same method will still apply. Okay, so in both of these cases, we're only missing 1 eigenvector. If, however, we get a case like case 3, 1 eigenvalue repeated 3 times, but it only produces 1 eigenvector. So now we're missing 2 eigenvectors and thus 2 solutions. We need to approach this a little differently. So there's a lot going on down here. So let's go through this. These will be the forms of the solution. So x1 is the same. x2 is the same. Okay, so we'll still get our original solution based on v. We'll get our other solution just like in the other cases up above. And then we have x3. So x3 is the new one. So this has a similar form to this one. We're just kind of establishing new pieces on top of that. So we've got e to the lambda t, w3 plus t w4. So that part is the same. Plus 1/2 t squared w5. Okay, and this is because we now have a third vector coming in to join in this case, where w3, w4, and w5 are to be determined. So the relationship with w3, 4, and 5 is very similar than the case with w1 and w2. So w4 is a minus lambda I times w3. Okay, so w3 times a minus lambda I gives us w4. w5 is a minus lambda I times w4. So we go one step further there. So in other words, it's a minus lambda I squared times w3. Okay, so 2 steps from w3 to w5. And a minus lambda I cubed times w3 is the 0 vector. So we're still taking the same pattern, but now there's one extra step because there are now 3 vectors here, not just 2. So we choose w3 such that a minus lambda I squared times it is non-zero, right? Because that would be w5. But a minus lambda I cubed times it would be the 0 vector. Right? So we're still choosing our w3, and the process of choosing it remains very similar. And we'll see how that looks in our upcoming example. Solve this system with this given coefficient matrix A. Okay, so we're solving a system of differential equations. We have the coefficient matrix A, and I went ahead and got the values of lambda already. So this one does give us 3 eigenvalues, but it's the same eigenvalue repeated 3 times. So we have -2 with a multiplicity of 3. We need to take a look at how many eigenvectors we're going to get out of this. So we take the null space of a minus -2i, so that's plus 2i. So that's going to be 1, -1, and 0 on the main diagonal. Everything else will stay the same. Notice the first row completely will eliminate the third row, and then when we try to add it to get rid of this value, we end up getting 1, 1, 0, 0, 1, 1, and 0, 0, 0, all augmented with the 0 vector for the null space. So we get an eigenvector, one free variable, that gives us the t, subtract that's -t, and then that becomes a negative, so we add, that gives us positive t, so we get 1, -1, 1. So we have only one eigenvector. All right, so this is exactly what case 3 is meant to deal with. So we know x1 already, right? So our first solution is the standard one. So that's e to the -2t times 1, -1, 1. No problems there. And we know that x2 of t will be e to the -2t times w1 plus t times w2. So we're going to need to make some choices here. To do that, let's take a look at some of these matrices. So notice, so a plus 2i is, we already found that, so that's this matrix right here. And a plus 2i squared. If we perform the matrix multiplication, so multiply this matrix by itself, we end up with -1, 0, 1, 1, 0, -1, and -1, 0, 1. So when it comes to our choice, so we're going to choose W1. We want W2, so when we multiply it by this one, we want to create an eigenvector. So that's one that looks like this, 1, -1, 1. So notice our middle row here, that is basically that just the same eigenvector. So if we created a vector like this, 0, 1, 0, this basically, when we multiply it, is just going to take the middle column, and that's going to be W2. If we multiply this by a plus 2i squared, we take the middle column, which is all zeros, and that's exactly what we needed. We needed to produce the 0 vector. So choose this to be W1, then W2 is 1, -1, 1. Okay, by multiplying by this, and a plus 2i squared times W1. Again, it takes that middle column, so it does give us the 0 vector as required. So that's going to give us x2. So we're going to get e to the negative 2t, 0, 1, 0, plus t times 1, negative 1, 1. Now we come to the new piece. We're going to need W3, W4, and W5. We already have a couple of the matrix multiplications up here, so notice if we took a plus 2i cubed, so we multiply this matrix by this one, okay, that's what makes it cubed. Perform the matrix multiplication, we end up getting the 0 matrix. Okay, which will be helpful for us. So we go ahead and choose W3. We need a choice for W3 that makes W5 non-zero. So, right, because W3 will multiply it by a plus 2i to get W4. We'll multiply it by a plus 2i squared to get W5. And then multiply it by a plus 2i cubed to get the 0 vector. So that's not a problem. Okay, so this will give us the 0 vector no matter what. We can't let this one take that column, so we can't use the same vector again, 0, 1, 0. That would give us 0 too soon. So what if we tried 1, 0, 0? So then W4 would be, this is basically just grabbing the first column of this one if you do the multiplication. So it's 1, negative 2, 1. And W5, if we multiply by this matrix, it again just grabs the first column. So W5 is negative 1, negative 1, which is non-zero, right? And that was the whole point, is we're trying to not get a 0 vector here. But then if we multiplied by this one, we would. So I can say, and a plus 2i cubed times W3 is the 0 vector. That gives us our form for x3 of t. So that's e to the negative 2t times 1, 0, 0 plus t times 1, negative 2, 1 plus 1 half t squared, negative 1, 1, negative 1. And that is going to give us everything we need. We had a 3 by 3 coefficient matrix here, so we should be getting 3 solutions out of this. We got x1 at the beginning. That was our straightforward solution from the eigenvector. We got x2 right here using the method from the previous example, and we got x3 right here using the new method that we just developed. So our general solution, and as with all these cases, the more complicated the process gets in solving, the longer these answers get. So we get C1 e to the negative 2t times 1, negative 1, 1 plus C2 e to the negative 2t times 0, 1, 0 plus t times 1, negative 1, 1 plus C3 e to the negative 2t times, just bring all this in here, go. And this will be the general solution to this system of differential equations that had a defective coefficient matrix A. If you want, you could combine these if you want, like make this all one vector, combine this into all one vector. If you want to like condense and make it a little bit smaller of a solution, but it's all equivalent. So I just kind of kept it in its regular standard form there. But that is the end of section 9.5. And so that is our introduction into solving these systems of differential equations, again, with a defective coefficient matrix.